Okay, so we begin with the design of a modulo counter. So for number one, so let us design a modulo 8 counter using an edge-sensitive flip-flop. So for this counter, so we have here our present state. So we have y1, y2, y3. So present state 0. Then its next state is 1. Then if your present state is 1, so the next count is 2 or 0, 1, 0. Then for present state 0, 1, 0 or 2, its next state is 3. So for the flip-flop input, so we all know that the input D is the same as our next state Q plus. So therefore, for our first flip-flop dy1, so that this is our next state, so that is 0, 0, 0, 1, 1, 1, 1, 0. So we have here 0, 0, 0, 1, 1, 1, 1, 0. So the same way dy2. So we apply this equation again for next state y2. So we have our flip-flop inputs for dy2 as 0, 1, 1, 0, 0, 1, 1, 0. So the same thing as for dy3 or flip-flop inputs for dy3. So next, let us draw our circuit for our modulo counter. So we have here our dy1. So we're going to get our equation using K-map. So let's say this is our y1 and this is our y2, y3. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So we have here for dy1 0, 0, 0, 1. So that is 0, 0, 0, 1 for input 0. Then we have 1, 1, 1, 0. So 1, 1, 1, 0. So we perform K-map. So here we have for this one. So we have here y1 y1 prime, y2, y3. Then we have here y1, so y2 prime. Then also we have here equation y1. Then we have y3 prime. So the equation for dy1 is y1 y2 prime plus y1 y3 prime plus y1 prime or complement y2 y3. So also for dy2 and dy3, so we will do the same, applying K-map. So for dy2, so we have 0, 1, 1, 0, 0, 1, 1, 0. So our equation for dy2, so we have dy Y2 is actually Y2 prime Y3, Y2 prime Y3 plus Y2 Y3 prime, or this is actually Y2 XOR Y3. So next we do again the same for dy3 for our third flip-flop. So we have dy3 so for dy3 we have here 1 0 1 0 1 0 1 0. So that is 1 0 1 0 1 0 1 0. So let's do mapping for this one. So we have here dy3 is equals to so y1 cancels. So we have y3 prime. Then we will use this equation to draw our circuit. Then that circuit will be used to derive our code for our Verilog. So here we have 1 2 3. So 3 and 8. And an OR gate. And that will be our input for our first flip-flop dy1. So this is our y1 flip-flop. So this is our input D. So we have our clock. So we have here y1 prime. So first we have here y1 and y2 prime. So I will write here negative y2. This is positive y1. So this means this is inverted. So here I have plus y1. Then I have here minus y3. Next I have 3 input AND gate. So I have here minus y1, y2, and y3. Okay, then for the next D flip-flop, so I have here XOR gate. So we do implement it using an XOR gate. So that will be an input to our flip-flop y2 or dy2. So this is your D. This is y2. This is also your y2 and y2 NAND. Okay, so your clock. So we have input y2 and so plus y2 plus y3. Next for our third flip-flop, so we have here our y3, and that is actually a wire coming from minus y3. So this is y3 NAND, or this is actually minus y3 plus y3. So we have a synchronous circuit. So clock are connected common. So we have a common clock for the circuit. This is our clock. So now let us write our code for the circuit. So we will use here a separate module for our flip-flop. So first let us create our code. So let's make use of a structural modeling for this one. So we'll name it module mod 8 underscore counter. So we have our input clock. So let us put some other inputs such as a reset. So if you want, if your component has a reset or the flip-flop has a reset, let's put here reset input. So our inputs are clock, reset, N. First we have our input Y1, Y2, and Y3. So let us define our input again. So we have our clock, reset, N, and for the output we have Y1, Y2, Y3. So we're going to instantiate using our built-in primitives, this component. So let's make it our, so this is 1, 2, 3, 4, 5, so this is our 6, 7, and 8 component. So let's say we want to use an AND gate. So let's say AND to input. Let's say instantiate natin si first logic gate, which is an AND. So let's say this is our wire. So let's name it net 1. This is net 2, net 3, net 4, net 5. So inst net inst 1. So for our AND gate, so the output is net 1. So its inputs are Y1 and not Y2. So we write here Y1, not Y2. Next we have our second component, which is an AND gate, 2-input AND gate. So that is instantiate our second component with input Y1 and Y3. So the output is net 2, so this is net 1. So inputs are Y1 and not Y3. Then for our third component, so that is 3-input AND gate. So let's say AND 3, instantiate 3, output is net 3, inputs are not Y1, Y2, and Y3. So these are for these components AND gate. Then we have, lastly, we have the 3-input OR gate. So we have here OR 3, ins 4. So the output is net 4, inputs are net 1, net 2, and net 3. Then we have here XOR, so that is XOR 2. So our fifth component, the output is net 5. Then its inputs are Y2 and Y3. Now we have here our D flip-flops. So for our D flip-flop, so suppose our module for D flip-flop is named as, so let's say we have another module for that D flip-flop, so let's say DFF, or let's make it DFF flip-flop. So for that flip-flop, so we're going to perform or instantiate that flip-flop in this module. So we use its name, so DFFE, so that is DFFE. So that is 6. So int 6. So the output is, so based on sa ating equation for DFFE1, so that is Y1, Y2 prime, Y1, Y3 prime, YY prime, Y2, and Y3. Then making use of this circuit as our basis, so that is actually output is, so here we have Y1, then so we have net, so we have net int 6 is so int 6 net 5 Y1, so we have here Y1 net 4 net 4 equal input, output is Y1. Then we have our clock and our reset N for that flip-flop. Then DFFE, our next flip-flop, 7. So we have output Y2. Then input is net 5. Net 5. Then we have here clock, reset N. Then DFFE. Okay, so we have the 8. So we have here output Y3. Then the input is not Y3. So not Y3. Then we have the clock, reset N. Then that is the end of our module and module. So this is the program or the Verilog code for this circuit. Okay. So for the test bench, so we can write a test bench for this one. So we initialize, so we generate display variables such as, so we use the initial, okay, so for the test picture, so use display variables. Let's say our display variable for this example. So we have the initial, then monitor. Okay, so format for our output is y1, y2, y3. That is %d. So we have y1, y2, y3. Then we generate a reset of initial, then begin at, let's say, at 0, so reset n is 1, then at clock 2, reset n is 0, then at, let's say, clock 5, reset is 1. So begin, end. Our test picture. Then we start our clock. So initial, begin. So let's choose clock is equals to 1 or 0. Then let's make it for network. Then let's say 10 microsecond delay clock. So clock. Is equals to that. So this is our clock. So that gives us this wave. Then now we can instantiate or determine our simulation. Okay, so we will do this one using Xilinx. So again, we're going to implement this code using our Xilinx. So here I coded first the Flipflop. So next, so this is our code. We generate with the circuit. The next, so I have created a test bench for this one. Okay, so that I will generate. So our objective is to produce a mode 8 or Modulo 8 counter that counts from 0, 1, 1, 2, 2, 3, and so on. Then, so that simulate using Xilinx. So here I have here my simulation. So I run it again. So since there's no error, so now here's the output for our counter. So as you can see, so here is our counter. So let's change the radix to a decimal. So as we can see, so it counts from 0, 1, 2, 3, 4, 5, 6, 7, then it will repeat. Okay, so that ends our presentation. So I hope you have followed. So what we need to do, so to code the circuit using Modulo. Okay, so here's the process. We have made to simulate or synthesize this circuit using mod 8 counter.